A continued fraction is a representation of a real number in the form shown here. Mercifully for typesetters, it can be written in compact notation as a sequence of numbers like this: A0, A1, A2, A3, and so on, where the integers a sub I are called partial quotients. Although you won't often come across them in school and even college math courses, continued fractions provide one of the most powerful and revealing forms of numerical expression. Numbers whose decimal expansions look bland and unremarkable suddenly turn out, when unfolded as continued fractions, to possess extraordinary symmetries and patterns. Continued fractions also offer a way of constructing rational approximations to irrational numbers, and discovering the most irrational numbers. Continued fractions first appeared in the works of the Indian mathematician Aryabhata in the 6th century. He used them to solve linear equations. They re-emerged in Europe in the 15th and 16th centuries, and Fibonacci attempted to define them in a general way. The actual term continued fraction first appeared in 1653 in an edition of Arithmetica Infinitorum by John Wallis. Their properties were also studied by one of Wallis's English contemporaries, William Brouncker, who along with Wallis was one of the founders of the Royal Society. At about the same time in Holland, Christian Huygens made practical use of continued fractions in his designs of scientific instruments. Later, in the 18th and early 19th centuries, Carl Gauss and Leonhard Euler delved into many of their deeper properties. Continued fractions can be finite or infinite in length. Finite continued fractions are unique so long as we don't allow a quotient of 1 in the final entry in the bracket. For example, we should write a half as 0, 2, rather than as 0, 1, 1. We can always eliminate a 1 from the last entry by adding to the previous entry. If continued fractions are finite in length, then they can be evaluated level by level starting at the bottom, and will reduce always to a rational fraction. For example, the continued fraction 1, 324 is equal to 40 over 31. However, continued fractions can be infinite in length, in which case they produce representations of irrational numbers. Here are the leading terms from a few notable examples of infinite continued fractions. These examples reveal a number of possibilities. All of the expansions have simple patterns except that for pi, which was first calculated by John Wallis in 1685 and has no obvious pattern at all. There also seems to be a preference for the quotients to be small numbers in these examples. The continued fraction for e was first calculated by Richard Coates, the Plumian Professor of Experimental Philosophy at Cambridge, in 1714. If an infinite continued fraction is chopped off after a finite number of steps, then the result is a rational approximation to the original irrational. For example, in the case of pi, chopping the continued fraction at 3, 7 gives the familiar rational approximation for pi of 22 over 7, equal to 3.1428571. Retaining two more terms leads to 3, 7, 15, 1, which equals 353 over 113, equal to 3.1415929, etc., which is an even better approximation to the true value of pi, 3.1415965, etc., and one that was known to the early Chinese. The more terms retained in the continued fraction, the better the rational approximation becomes. In fact, the continued fraction provides the best possible rational approximations to a general irrational number. Notice also that if a large number occurs in the expansion of quotients, then truncating the continued fraction before that will produce an exceptionally good rational approximation. Most continued fraction quotients are small numbers, 1 or 2, so the appearance of the continued fraction of pi of a number as large as 292 so early in the expansion is unusual. It also leads to an extremely good rational approximation to pi. 3, 7, 15, 1, 292 equals 103,993 over 33,102.